So today we are beginning our new unit on motion. So we're starting with notes 7A. If you are at home watching this, please either use the document that's in today's folder, which is Wednesday, November I don't know, whatever day it says note 7A, November the 9th, 8th. Yeah. Go into that folder and you can type in the words, or if you missed and got a paper copy from me, hopefully you've got the paper copy right in front of you and you can just fill it in using the video. All right. So I want to get rid of that so we can see. There we go. So first we have up here on this area, it's the quick review. It only has three words: distance, speed, and time. I want you to take a second to figure out what goes where. So pause the video, figure out what goes where. All right, welcome back. Here we go. This is what goes where. So speed is calculated by dividing distance by time. And the formula looks like this: speed equals distance over time. And you know this already from the fact that speed is expressed like miles per hour. So miles being a distance, per being what the division line means, and then hour being a time. Miles per hour helps us to remember the formula for calculating speed, distance over time. Make sure you have that written down, and I'm going to clear it. So, how do we know when something's in motion? Think about that for a second. Like, how would you know that the ball was getting ready to roll to your feet? How would you know that the pencil was getting ready to roll off the desk? Right, like the desk is still and the pencil keeps rolling, is moving. So you know if something is moving if you see it move in relation or relative to another object. So the desk is still, the pencil rolls, the pencil falls off. The ground is still, you are still, the ball is coming toward you. So you know that the ball is moving towards you. You know it is moving. So an object is in motion when its distance from another object is changing. That means that motion is a relative term. Whether or not something is in motion is determined by comparing it to something else. So right now, you, me, the lab tables, whatever place you are in right now, we're all in motion. So this room, this entire school are all moving at approximately 30 kilometers a second. 30 kilometers a second. That's really fast. That's like 60 miles an hour. It's really fast. 70 miles an hour. How is this possible? How are we all moving that fast? Exactly. Because the earth is spinning on its axis. As it goes around the sun. So we have two movements there. We have the spinning on the axis, and then we also have the fact that as it's spinning on its axis, it's going around the sun. Do we feel that motion? No, of course not. Why not? Think about what the definition of motion is, how we determine motion. Exactly, because everything on earth is going that speed. So there's nothing relative to it to compare it to besides the stars that are very distant, and that's how we know how fast we're going. So everything on earth is moving at that speed. Hello, endpoint antivirus. Bye, Endpoint Antivirus. All right, make sure you have that. I'm clearing it. Pause it if you need to. So that makes measuring motion difficult. So what do we do? Physicists use motion. Physicists that study motion use something called a reference point. So if you're studying the motion of the stars, you pick a star that's distant and is so far away that it seems to not move, and then you look at the other stars that are closer and see how they move in relation to that star. A reference point is a place or object used for comparison to determine if something is in motion. An object is considered to be in motion if it changes position relative to the reference point. So, like I said, distant star that is so far away it doesn't seem to move. It's our fixed spot, and then we see how the other things relate to it. If we're measuring a track team, how fast they go, the one person stands and measures the time it takes for them to get back around to the line where they started. Speed is defined as the distance the object traveled per unit of time. Speed is a rate. This means it tells you the amount of something that changes over a given unit of time. Rate is always determined by time, some unit of time, plus one other measurement. So if I wanted to measure how many students pass my class per year, that would be a rate because it was over time. It's over a year. If scientists wanted to see how many planets moved past a certain point within a millennia, that would be a rate because it's over time. Now, is it an absurd amount of time to us? Yes, but it is indeed an amount of time. Okay, so here we've got circle it if it's a rate, X it if it's not. 72 jelly beans per bag. Is that a rate? No, it is a proportion, but it's not a rate because it doesn't have a unit of time. How about 14 gallons per minute? Yes, that would be a rate because it is a unit of time. All right, you look at 3 and 4. Seriously, pause it and look at 3 and 4. Okay, welcome back. Here we go. Yards per minute means it's time. Per glass means it's not a rate. It is a proportion, but not a rate. What was our formula for speed? Right. I feel like Dora the Explorer. S equals D over T. Speed equals distance over time. So let's calculate the speed for a horse then that galloped 3 kilometers in 10 minutes. So we've got speed equals 3 km over 10 minutes. And we put that into the calculator, and we know whenever we're dividing by 10 or 100, we just have to move the decimal. So there's 1 0, so we're going to move the decimal one place. So the answer would be 0.3 kilometers per minute. Again, pause it if you need to. I'm clearing it. If you calculated your speed on the way to school this morning, you would measure the distance from home to school and then divide that by the time it took to get here. However, did you travel at the same exact speed the entire time from the moment you got into the car until the moment you arrived at school? No, especially if you had to drive through Crewe or Blackstone. Like, you have to slow down through town like that. So what you are getting when you do that is an average speed. So what you did was calculated your average speed. You took your distance by the time it took, and that gave you the average speed that you traveled. Now, what about things that are really big, like ships and trains? So they usually do move at the same rate of speed for a long time. A ship doesn't have to slow down to go through town in the middle of the Atlantic Ocean. So it can just kind of chug along. And that's called constant speed. So when something like a ship or a train is able to maintain a constant speed, it's not altered for basically the entire time of the travel. That is called constant speed. When a police officer uses a radar gun, a radio frequency detection and ranging, does the radar know how far the car traveled? Like, does the radar know that it was this long, that you'd been on the car for this? Of course not. So when that happens, it's instantaneous speed. So it is taking the speed in that exact second. How fast is that vehicle going in that exact second that the gun hit it and sent them the messages back? It measures the speed in nanoseconds, like a very, very short period of time. All right, again, pause it if you need to. Speed in a direction. That D looks very strange, so I'm going to fix it. Is called velocity. To determine the velocity of an object, you have to know both its speed and its direction. Why is knowing the velocity of an object important? Like, just period, why is it important? And especially as you begin driving, why is it important to know the velocity of the objects around you? Right, exactly. So you can move when it's coming at you. So that if you, especially as you're driving, if a car is slowing down that's in front of you, you can slow down so you don't rear end it. So that if a car is coming from the side, you can again be aware of its motion. If a little kid is chasing after a ball, you can stop because you know that kid might run out in front of you. So understanding velocity is very important, so that you can move in response. So you want to be able to do whatever thing you've got to do to protect yourself or keep people safe or whatever. All right, pause it if you need to. I'm clearing it. Meteorologists. Meteorologists use velocity to predict the path of storms. Air traffic controllers use velocity to predict the path of airplanes, giving pilots new coordinates when necessary to avoid collisions. So we've got velocity being used by looking at the at the cloud patterns and which direction are they going and how fast, so that the meteorologist can tell you that we're going to have rain on Tuesday or snow on Thursday or whatever. Air traffic controllers definitely need to know the velocity because they need to be able to move planes up, down, sideways, around, because they've got more space than just the plane of a road. They've got all the space to deal with. So they need to understand the velocity of what's going on. All right, so our discussion started with speed, which is a rate of distance over time. And then we added that velocity is speed in a direction. And now we're going to add our next vocabulary word when talking about motion and talk about acceleration. And that's probably the most misunderstood one. Acceleration. So acceleration is the rate. So yet again, that means it involves what? If it's a rate, it has to use time. Exactly. So acceleration is the rate at which velocity changes. So acceleration is any change in speed or direction. So this is where people get confused because you think acceleration, you think speeding up. Boom, easy, right? Well, that one's the easy explanation, but there's actually two other things that are considered to be acceleration. You're tardy. Okay, so acceleration can be an increase in speed, a decrease in speed, which is the one that boggles everyone's mind, but that's a change in speed or direction, right? And changing direction. All right, pause if you need to. I'm erasing it. All right, so increasing speed. This is the one you're familiar with. When you think accelerate, you think acceleration, you think speeding up, and that's the one that is the most easily understood. When you're riding in a car and you're getting onto a large road that has an entrance ramp, there is something called an acceleration lane. Now, I'm going to draw. You do not have to draw on your paper. But, we're tooling along. Here's 460, and you're getting ready to get on 460. And so there's this lane that's added. And this whole time while you're driving in your little car on this, you're supposed to be increasing your speed so that by the time you get to here, where everybody else is supposed to be going 60, because that's the speed limit, you're up to 60 or at least getting close to it so that you can merge with traffic. So it's called an acceleration lane. All right, so what are cars riding supposed to do in that lane? Right, they're supposed to speed up to join the flow of traffic. All right. Here's where it gets weird. So, decreasing speed. So, motion which speed decreases is also considered acceleration because it's a change in speed. I know it's weird. It's sometimes called negative acceleration, just to try to avoid confusion, or deceleration. So when you're studying to get your license, the DMV manual will call it deceleration in an attempt to avoid confusion. So again, when you're riding in a car on a highway and you need to make a turn, another lane is added for a few yards leading up to the turn. So yet again, we're going to pretend we're on 460. And up here is, I don't know, CCC Road, or I don't even remember one of the roads. But in this area leading up to where CCC Road turns off, there's this extra lane added over to the side. And cars that are wanting to turn onto this road are supposed to slow down, and then are supposed not slow down here though. They're supposed to just barely begin slowing down here and then really do their slowing down here to make their turn. Again, so that they're not impeding the flow of traffic here, so that the people that are going 55-60 can keep going 55-60, and then you that are turning get out of the way. Now, do people do that all the time the way that they should? No. I don't know how many times I end up having to brake because a person didn't decide to slow down, or didn't decide to use the deceleration lane. They decided to just do their slowing down in the main lane, and then they just barely at the end get over into the turning lane. Really frustrating. All right, so what are cars supposed to do in that lane? Right, get over, to slow down, to turn. All right, again, pause it if you need to. I'm clearing it. And then finally, changing direction. So we know that velocity is a change in speed or direction. Acceleration and a change in speed or direction, because velocity is speed in a direction. So that means that changing direction is also accelerating. When you're riding in a car along the highway at a constant speed, common knowledge would say that you are not accelerating because you are not changing your speed. Remember, however, the definition of acceleration. It's the rate at which velocity changes. And then the definition of velocity, speed in a direction. So acceleration is a change in either speed or direction. So a car that goes around a curve or changes lanes is accelerating, even if it's done at a constant speed. Crazy, huh? Science with their crazy definitions. Wait till we start talking about heat versus cold. Will blow your mind. Anyway, all right, so we're going to circle it if it's an example of acceleration. We're going to cross it out if it's not. Again, please pause the video and do them and then come back so that you can test yourself out. I really, really recommend it, because later on, when these show up again on the quiz and test, you're going to be much better at identifying them if you got it right or wrong on your own this first time. So I really challenge you to pause the video and do this on your own, okay? All right, here we go. A runner slows down after crossing the finish line. So that is definitely acceleration. It is negative acceleration because he is slowing down. A leaf falls from a tree. So that is a change in speed. So the little triangle thing, it's delta. And in physics, that's the symbol for change. So change in speed. A leaf falls from a tree and is blown to the side by the wind. So we definitely have acceleration there. We have a change in direction. So it probably was falling at a constant speed because, or nearly constant speed, but then the wind accelerated it, changed its direction. A train travels at a constant rate of speed. A train travels at a constant rate of speed. Well, there's nothing there about anything changing. So that would be no change. That would not be acceleration. A horse adds a burst of speed to win the race. Definitely acceleration. That's a change in speed. All right, what about a shark quickly darts right and snags his prey? Yep, he was traveling straight and then he jogged to the right. That is a change in direction. That is acceleration. A goose flies at a constant rate of speed. Constant rate of speed, there's no change. So it is not acceleration. A tractor trailer applies brakes as it approaches a stoplight. Tractor trailer applies brakes as it approaches a stoplight. It's slowing down. That's negative acceleration. So it is acceleration. It's a change in speed. And finally, a drag racer sees the green lights light up and hits the gas pedal. He definitely accelerated on that one. That's kind of our very definition of acceleration, isn't it? All right, so pause those to make sure, pause if you need to check and make sure you got those right, but I'm going to erase and move on. All right, for these last two, I had to move the camera out of the way. Oh, well, maybe I can. Yeah, there we go. I can put it up there. Okay, so the last two, we're going to calculate the average speed. So we've got a train traveling on a 750-kilometer sightseeing loop. It arrives back at the station 4 hours after it leaves. So you don't have to write all of this part down, but just I want to show you where the work's coming from. Speed equals distance over time. So the distance is 750 kilometers. The time is 4 hours. 750 divided by 4 is 187 and a half. And then we have to include kilometers per hour. So hang on, let me grab my calculator and I'll show you if it'll show up. I guess we'll see. 750. Did it show up? Yay, 750 divided by 4 equals 1875. All right, cruise ship travels 10,000 kilometers in 12 days. So now it's going to be 10,000 kilometers divided by 12 days equals 10,000 divided by 12 is 833 and a half kilometers per day. That is impressive. Just saying. I think maybe Miss Harris was really making up some numbers on that one. They don't travel that far. And then finally, you're going to make up your own speed story and calculate speed. Please, feel free to get creative. Just keep it school appropriate. The one that the student wrote that I have in front of me as an example, the cheetah ran 10 kilometers in 5 minutes. Its speed was 2 kilometers per minute. So something along those lines. Want you to fill in that section there, make up your own, and do the math using a calculator. All right, that is it. We will continue the rest of what we're doing in class. Hopefully, if you're doing this on your own, this was all you needed. I hope that you have a lovely day and that you make good decisions. Bye.